Hello once again, everyone. This is Mr. V. Hill. Today we're going to be talking about simplifying rational expressions. And we've already talked about a little bit about rational expressions or rational functions, if we write them a certain way. It's where we have one polynomial divided by another polynomial. And really, this is going to be just like simplifying rational numbers. Like 2/4 you rewrite as 1/2. You just cancel the common factor of 2 in both the numerator and the denominator. So we're going to be doing the same thing here. So if you have a common factor in the numerator and the denominator, we can just cancel that out. And so, first example we want to look at, 6x plus 12 over x plus 2. Now keep in mind that this vinculum is a grouping symbol, so technically speaking we have parentheses around both the numerator and the denominator, which we don't need to write because of the vinculum. But notice here that the numerator has a common factor of 6 in both of those terms. So if you factor that out, what we'll have left inside there is going to be an x there, and then a factor of 2 in the 12. So the numerator is actually 6 times x plus 2. And of course we have this factor of x plus 2 also in the denominator. And so we can cancel these two factors out, sort of. So basically this entire expression really breaks down and simplifies just as to 6, so long as x does not equal -2. Because if x is -2, we will have a 0 here in the denominator, but we can't divide by 0. Even though that would make the numerator also 0, but 0 divided by 0 is also just as undefined as any other number divided by 0. And one way to look at this here is if we were going to graph it. Just go into here and we'll type this in. Remember, when you're putting it into your calculator, you have to put parentheses around both your numerator and denominator. 6x plus 12 divided by a factor of x plus 2. And if we just graph that in a regular window, we see that, yeah, now that'd be looking at y equals this expression. So now the y, which is this whole thing, is always equaling 6. But remember, we did have this restriction here that x could not be -2. So what we can do here is we can change up our window a little bit. Here we can go zoom. Go zoom decimal. Oops, we can't see a darn thing now. The window changed, but what it does when you hit that zoom decimal, it changes your ranges on your x and your y. So here what we're seeing is that our x's are going from -4.7 to 4.7. The reason for that is that there are 94 pixels across the screen. The y's are going from -3.1 to 3.1. That's because there are 62 pixels going vertically. So when we do this zoom decimal idea, what it does is it puts 1 pixel for each tenth. So if we want to change this up a little bit, we're going to need to see at least 6. So if we just multiply each of these by 2 and go from -6.2 to 6.2 on our y's, now when we graph it, we're going to see 1 pixel every 2/10. So now when we graph it, yeah, it looks like still same thing. There's our line y equals 6, but you'll notice there's a hole right here at where x is -2. So again, that's a removable discontinuity. We remove the discontinuity basically by canceling those two factors. But that's for another day. So basically, this expression simplifies down to just 6, so long as x does not equal -2. And when we do this, we have to specify the restrictions on x while we do this. Let's do another example, just to show you something that sometimes pops up. If we have the expression 6 minus 2x over, let's say, x minus 3, well, now we have a common factor of 2 in the two terms in the numerator. So if we bring that out, this would be 2 times 3 minus x in the numerator and we still have an x minus 3 in the denominator. Now it looks like nothing's going to cancel out until we notice that 3 minus x is exactly the negative of x minus 3. So instead of doing it this way, what we could do is if we rewrite this as negative 2x plus 6 over x minus 3, and now if we factor out a negative 2 in the numerator, we're going to be left with x in that term, and then minus 3, because of course negative 2 times a negative 3 is what gives us that positive 6. And we still have this x minus 3 in the denominator. And so again, this is going to cancel out. And so the whole thing is equal to negative 2, but we have to specify that we can't have a denominator of 0, so x cannot equal 3. And again, if we were to graph this, clear this guy out, it's going to be 6 minus 2x in the numerator divided by x minus 3 in the denominator. If we graph this thing, yep, now it's looking like y is equal to negative 2 always, but if we look really close, there is our hole in the graph. There's a removable discontinuity when x is equal to positive 3. Okay. Let's try something slightly more complicated here. Call this one example 3. Sorry about that bell. Let's try 3x squared minus 9x. That'll be our numerator. And then x minus 3 again is our denominator. Now, if we factor this numerator, see a common factor of 3x in both of these terms. So the numerator factors as 3x times x minus 3. Check that just by multiplying this back out. 3x times x, there's our 3x squared. 3x times negative 3 is our negative 9x. And then we still have this factor of x minus 3 in the denominator. And so, notice here, x minus 3's will cancel. So this whole thing is equal to 3x, so long as x does not equal 3. So let's graph this one just to see here. 3x squared minus 9x, in parentheses, that's our numerator, divided by x minus 3 in the denominator. And if we graph this thing, oh wait, let's go back just to zoom standard. A regular old negative 10 to 10 on both axes. And there we see the line y equals 3x. Going through the origin, because it's a direct variation, and a slope of 3. Now we're not seeing the discontinuity here. That would happen when x is equal to 3. Then if we try a zoom decimal, we're not going to see it again because, well, x is 3 would be way up here off of our screen. So we just adjust our window a little bit. I'm just going to change around the y values. I'm going to go from 0. Now if I do 6.2, that won't quite be enough. So here we have 6.2, so there would be 62 pixels. There would be 1 pixel for each tenth. If I multiply that by 2, and I just go up to 12.4. Now we're going to see it because, of course, when x is 3, this thing should be 9. So now if we graph, there it is. There's the line y equals 3x, and we see a hole in the graph right there when x is 3. One last example. Let's try x squared minus 16 over x squared plus 8x plus 16. Both the numerator and denominator will factor now. Numerator, x squared minus 16, that's a difference of squares. So this is just x plus 4 times x minus 4. Denominator, two numbers that multiply together to give us 16, but add together to give us 8. Again, 4 and 4. So this is x plus 4 times x plus 4. And now here, those factors are going to cancel, leaving us with the expression x minus 4 over x plus 4. But again, we still have the restrictions from both these. Luckily, they're both there still. We know that x cannot be negative 4. Again, so let's graph this thing just to see what that looks like. The original one, not the simplified version. I'm trying to keep the glare off of it. Sorry. Yeah, let's go with numerator is x squared minus 16 divided by our denominator, x squared plus 8x plus 16. And now let's go just a regular window. Okay, and now we're seeing something more like a hyperbola here, just like those inverse variations. But we see the discontinuity is happening here at x equals 4. But this is an infinite discontinuity because this factor in the bottom did not get canceled out. So that's still going to be there. And instead of being a removable discontinuity, this is now an infinite discontinuity. And that's about it for simplifying rational expressions. See y'all in class.